This is the calculus video, but we have to talk about fractions first. Have a look right here. If I put down 1/2 plus 1/3, let me ask you, what's the most common wrong answer that people will say? Yes, 2/5, because 1 plus 1 is 2, and 2 plus 3 is equal to 5, right? Of course, not here. This is so bizarre. Because if you think about it, we did fractions when we were like 8 years old or so, right? And why is that we have to do what they call the common denominator thing? How come we cannot just add 1 plus 1 and 2 plus 3? So weird. But let's kind of fast forward a little bit. Let's maybe go into algebra or pre-calc. Let's look at this. This is called a matrix. That's that we have 1, 2, 3, 4. And then we are going to add it with another matrix. That's that we have 5, 6, 7, 9. All right? Well, in this case, if you just go ahead and add 1 plus 5 and get 6, 2 plus 6 you get 8, and then 3 plus 7 you get 10, and then this plus that you get 13. Guess what? You will actually get this right. Oh my god, seriously? This right here, it seems so much easier. Why didn't you tell me this like in 2nd or 3rd grade, right? Why did you teach me fractions and then how to struggle with the so-called common denominators and things like that? Oh my goodness. Well, don't worry, because today I actually have a way that I want to tell you guys that you can actually add fraction in a more logical way. Then you can just add the numbers that you see. And would you be interested in that? Sure thing, right? Alright, are you guys ready? Good. Okay, here we go, ladies and gentlemen. Here we have 1/2, and let me tell you, as long as you are willing to do some magical work, and you can say this right here is equal to 0.5. And then right here for the 1/3, as long as you are willing to do some magical work, you can actually get 0.333 and so on, so on, so on. I know, please do not turn off the video. I know you guys feel being trolled, but I have my point, right? Anyway though, once you change the fractions to what we call the decimals, can we add them easily? Yes, we can add them very, very easily. Just go ahead and add them correspondingly, right? 0 plus 0 is 0, and then 5 plus 3 is 8, and of course line out the decimal point, and then so on, so on, so on. And if you present this right here, wouldn't this be a legitimate answer? Yes, definitely, right? Now, let me tell you, I think we just have been so used to fractions and decimals, and we don't appreciate them anymore. And it's actually extremely useful. If you don't trust me on that, well, let me ask you, what if we want to do square root of 2 plus pi? How would you do that? As you can see, I know, yeah, we're all good, like get a common denominator, things like that. But for square root of 2 plus pi, if you want to have a sense of how big the numbers are, right, the result is, well, we better change this into decimal, and you will have to do some magical work. Square root of 2 is actually equal to 1.414, and it actually keeps on going forever. And then for pi, it is actually equal to 3.1415, and so on, so on, so on, right? Anyway though, once you change these two numbers into decimals, well, we can just add them up in a much more reasonable manner. 1 plus 3 is 4, 4 plus 1 is 5, and then the rest is just 5, 5, and so on, so on, so on. By the way, take a guess on what the next digit is. I'm not going to tell you. Anyway, this right here, again, it's a legitimate answer, right? Good. Well, I will tell you guys some calculus things. Let's take a look at this right here. Suppose today we are dealing with functions rather than numbers. Let's look at if we have the function 1/1 minus x. And I want you guys to add it with e to the x. Of course, they are common functions in calculus. And to add these two functions together, yes, we can just get a common denominator. But I don't even know how to get a common denominator with the regular fractions. You really think that I can get a common denominator for these two functions? Don't do that to me. But I will do this for you guys. Check this out. 1/1 minus x. As long as we're willing to do some magical work, and we can actually get this become equal to 1 plus x squared plus x to the third power, and so on, so on, so on. And ladies and gentlemen, are you guys ready for the next one? Hopefully, this right here, as long as we are willing to do some magical work, we can show that e to the x is equal to 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial, and then so on, so on, so on. Now as you can see, these right here are just polynomials, although they have infinitely many terms. But if you look at this right here, and if you want to add them up, can we just add them up correspondingly? Yes, check this out. 1 plus 1 is equal to 2, and we can do that legitimately. We couldn't do that with fraction earlier. And then for the next one, x plus x is 2x. And now, this is 1 x squared plus 1 over 2 factorial, which is 2. And then, 1 plus 1 over 2. Get your common denominator, okay? And then you get 3 over 2 x squared. And then this is 1 over 6. All right, 3 factorial 6, and then plus 1 altogether. Again, get your common denominator. You will get 7 over 6 x to the third power, and then so on, so on, so on. Well, again, this right here would be a legitimate answer, isn't it? Yes, definitely. So over here, I pretty much just use the decimal as an analogy to show you guys what this is all about. These right here are called the power series, and of course I'll write that down right here for you guys. And in fact, this is how I introduced the concept of power series to my Calculus 2 students. Right, so have a look right here. I want to tell you guys what power series is all about. As you can see earlier, decimal numbers make the computation so much easier, right? Well, that's what power series will do for us as well. They will make the computations so much easier for us. Like for example in this case, but let's talk about calculus. When we have polynomials, we love to do this, right? We love polynomials because we can differentiate them. We love to integrate polynomials because they're so much easier. So the goal for the power series is the following. So let me write that down right here. This is the purpose or the goal of power series. As you can see on the left hand side, we have functions that we might not like too much. I will consider these two as that complicated function, but on the right hand side, we have infinite polynomials because they have infinitely many terms, and they are polynomials because you see that we have x to the first power, x to the second power, and so on. All the powers of x, they are just positive whole numbers, and of course we have the constant terms. So the purpose of the power series is that first, we will represent, and I'll just say they are complicated functions. And what do I mean by complicated? Anything that's not polynomial, I will consider to be complicated. Because if you look at a polynomial, if you want to differentiate or integrate them, you can just use the power rule. How cool is that, right? So the purpose of this is to represent complicated functions with infinite polynomial, so that, and I will just tell you guys the following, many operations, or maybe if you want to do approximations, right, will be easier. That's pretty much the idea. Again, just take a look at this right here. And now, I would like to tell you guys what are the things that we'll be doing for power series. First, let me tell you what are the things that we need when we are working with power series. So right here, the first thing that we need, I will call that to be the form of the power series. And that's just simply how the power series look like, right? So remember earlier we were talking about when we have a power series, we are trying to write a complicated function denoted by f of x in general. Write this as an infinite polynomial. And when we have an infinite polynomial, we have the constant term. And the notation for that is C0. And then next, we have the x to the first power term. And it has a coefficient as well, so we'll just put down C1 times x to the first power. But in general, we may have what we call the different center. What I mean by that is the following. Well, this is our good old friend, right? Y is equal to x squared. But we can move this around. It will have a different center, right? Suppose I move it to here. Let's say this right here is 3. Then in that case, the equation becomes y is equal to x minus 3 squared. So in general, we'll write this as x minus a and then to the first power. So we'll use this as an input in general, and the a is called the center. And then next, we have the second degree term with the C2 as its coefficient, and then we have x minus a to the second power, and then so on, so on, so on, just like that. Of course, that is a lot to write. We don't like that. It's okay, because we can just use the sigma notation for it. So, to put this in the sigma notation, it will be the series as n goes from 0 to infinity. All the c's right here are the coefficients. So we write this down as Cn, and the input right here is the x minus a to the nth power, like that. So this right here is what I call the form of the power series. It's just simply how the power series look like. Let me write that down real quick. This is the first thing. This is just the form. And just like I mentioned earlier, the A right here is called the center of the power series. PS, not PlayStation, right? Power series. And the Cn right here, which is actually the hardest part to find out, because for the center, you just have to wait for the direction. Like, find the power series at A is equal to whatsoever, right? So this right here is usually given, but for the coefficients, you will have to do some work to find that out. So let me write that down right here. So let's say we have the coefficients, right? So how can we find the coefficients? I will tell you guys this right here, right? For the form in general, we have two ways to do it. This first way is we are going to use, right, what I call the best friend. Best friend. Right? So what's the best friend? Just like how I mentioned earlier, how can we use it? I will show you. Because if you have a best friend, you should know how to use it. I know it sounds so bad, but math is totally okay. Or the second thing that we can do is we can use what we call the Taylor formula. What's the Taylor formula, you ask? Well, that will be later on. In fact, this video is just to introduce you guys what power series is all about. I have done a power series marathon for you guys already, so I will have that link to in the description for you guys. I worked out 26.2 power series. After that video, you should be an expert on how to find the form and then the two other things that we need. Alright, so that's the form in general. Next, we need to know, because when we have a power series, sometimes we might not be able to plug in certain x values because there are restrictions. Those restrictions came from what we call the radius of convergence. And this simply tells you how far you can go out away from the center. So when you have the form already, usually you should indicate that, okay, we have this, and then also notice that the second thing is you should write down the absolute value of x minus a to be less than r. And the r is precisely the radius of convergence. How do we find that? Again, we can use the best friend, or maybe we have to do something else, but that will be later on. The third thing is that because when we have this inequality, we can open it. So this means what? Well, we have the center that's at A, and the radius in the one-dimensional situation, it tells us that we can go to the left and also the right r units. So right here, if we go to the left r units, this right here becomes at a minus r. If we go to the right at r units, we get a plus r. So as you can see, we end up with an interval, and the interval will tell you more information. So all the numbers inside of the interval are the legitimate x values that you can plug in into the power series, and that will give you the correct function for the f. But there's one little problem with this right here, this interval. First, let me write this down right here for you guys first. This is called the interval of convergence. And that's precisely the continuation of the second part, right? So once you have this, you should be able to get that. The trouble for this right here is the following, right? All right, let me write that down. When we see the picture, we can use interval notation for this, and the notation for the interval of convergence just I. Well, this right here will become, it goes from a minus r to a plus r. But the trouble is, do I include the endpoints or do I not include the endpoints? Parentheses with bracket. Well, let me show you guys this. Have you guys seen this notation before when you are working with interval notations? No? You should say no, because I just make this up. So, and the reason is because we have no idea if we are going to include the endpoints or not, unless we do more work. And those things, yes, we will have to do the ratio test, direct comparison test, alternating series test, things like that. So all the series convergence tests are used to check the convergence at the endpoints of the power series for the interval type. Yeah, so I will just say must check. Right? Must check with the convergence tests. Yeah, so this right here, just keep this in mind. We have the three things that we need: the form, the R, and also the I. But today we are going to finish this happily because we will look at the best friend right now. So we'll start with the geometry series right here. And this is the one that we are going to be looking at, starting with 1. And then we are going to add it with r, and then r squared, and then r to the third power, and then so on, so on, so on. Well, we know that the first term is 1, and then the common ratio is r. If this is nice enough, then this right here will converge to the first term over 1 minus the common ratio, right? And we know this right here is nice enough when the absolute value of r is less than 1. If this happens, then this right here will converge to 1 over 1 minus r, which is very nice. As we can see, the left-hand side is the expanded version. Of course, we can put that down into the sigma notation form. So it becomes the series as n, let's use 0 right here, and then infinity. Because n starts with 0, we can just write this down as r to the nth power. Just like that. Very nice. Now, take a look right here. Earlier, we put this down from left to right. Right now, we are going to look at this backwards. So I'm going to put this down first. So let me write down 1 over 1 minus. But instead of using r, I would like to use x. So we can look at this as a function. And now all we have to do is replace all the r's with x's. So we can see that this right here is equal to 1 plus x squared, and then x to the third power, and then so on, so on, so on, isn't it? And of course, we can also put the x right here, so we can get what? Yes, the series as n goes from 0 to infinity, x to the nth power. And we can also write this down as the absolute value of x has to be less than 1 in order for this to be legitimate. As you can see, this is the function 1 over 1 minus x. It's a rational function. This is the expanded version of the power series, and then we have also the power series in the sigma notation, and this is exactly the form that we need. So we have the first thing. And the second thing is that based on this, you can see Well, because it's x only, it's not x minus 4, so this right here tells us the center is at 0, and this right here tells us the radius of convergence is equal to 1, which is very nice. So just make a note right here. This expansion tells us the center is 0, and then the r is equal to 1. So nice, isn't it? All right. Now, this right here is exactly why I call it best friend. And nowadays, you can also call this to be the bestie, because I think this is a popular word nowadays, especially on TikTok. But I've been calling this the best friend for about like 5-6 years already. So I will, keep writing it down, best friend, like so. And I would really like to tell you guys why this is the best friend. Hopefully after all this, you may also want to call this the BFF, best friend forever. Anyway though, one reason that this is the best friend is because, you see, we actually have the power series already, but it will also help us to get more power series of more functions. In fact, I have a video called the Power Series Marathon, where I have done 26.2 power series for you guys already. I will link that in the description for your convenience. So I'm not going to work out all 26 again, because this video is just trying to introduce you guys the concept of power series. This is the first one, ladies and gentlemen. Have a look. Right? Have a look. So nice, isn't it? And I like to just assign things names, so that way we have some like better feeling about the questions, better feeling about the math. Because, okay, here's the deal. If I just call this the geometry series, people will be like, no, I don't want to learn it. But if I call this the best friend, which is actually really beneficial because it actually helps you to do a lot more. Best friend, who doesn't like best friends, right? And of course, when we have a best friend, we need to know how to use it. I know it sounds so bad, but in math, it's totally okay. Anyway though, I would like to explain to you guys this function and this right here, and also what the r represents. And by the way, we have this already, so we can draw the interval of convergence. The center is at 0, and then you see the r is 1, so we can just go to the left 1 unit, and then go to the right 1 unit, so we go from -1 to 1. And for the best friend right here, I would like to tell you, we do not include the endpoints. So you can just keep that in mind. Why? One way to do it is, you just put a 1 in here. Then just get 1 plus 1 plus 1 plus 1 dot 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 forever. That will give you infinity, so it does not converge. And the second thing you do is check -1. If you put -1 in here, well, that will also not be a convergence situation. You actually get, when you put -1, you get 1 minus 1 plus 1 minus 1, and then you get a weird sum, right? You get a weird series. It does not converge. One simple reason to say this does not converge is because, remember, for the geometry series, the absolute value of r has to be less than 1. But later on, be really careful with this notation when we do the other power series, because we really have to check the endpoints, right? The convergence at the endpoint. For the best friend, I can tell you the I goes from -1 to 1, and we do not include the endpoints, right? So that's that. Now, take a look at the graph of 1 over 1 minus x, which is just a rational function, and it has a vertical asymptote at 1. So let's say is right here. This is at 1. And the graph of that looks like this. Go up like so, and then go up like so. All right? Now, take a look at this. We have 1 for the first term, and if you just make a graph, y is equal to 1, that's just going to give us a horizontal line right here. And you will see the horizontal line cross the curve right here. That's it. Pretty boring, because they only intercept at one point. If you include the next term, which is Now 1 plus x. If you graph this right here, you get what? You get a tangent line right here. And that's the calculus term for that. You get a line tangent to the curve at x equal to 0. X equal to 0. That's exactly the center right here. Could you have different centers? Yes, but you will have to change the form of the power series. And again, you will have to watch the power series marathon to find out how to do it. Anyway though, as you can see, this right here is the curve and this right here is the tangent line. And if you look at the line and then the curve, they are pretty close to each other around this region right here, right? Okay, and that's the one way to approximate the curve, the linear approximation, right? Locally speaking. Can we do better? Of course, because we're in Cal 2 now. And to do so, you know what? We have a lot more terms right here. All we have to do is just keep putting more and more terms. And let me show you guys another picture right here real quick. Suppose we do that picture again, which is 1 over 1 minus x. And then again, we have the vertical asymptote. And then we have this right here. Bad picture, I'm sorry. But yeah, you get the idea. Okay. Well, earlier we have this, right? Y is equal to 1 plus x. Now, if I want to graph y is equal to 1 plus x squared. So let me just write that down here. Y is equal to 1 plus x. And then we want to add one more term, which is x squared. So what does this do? Well, you can think about the following. The center is like your starting point. The approximation, like the line right here, will touch the curve right here at this point. All right? And then after you add more and more terms, what you are doing is that you are going to bend the line. You are going to bend the line so that the red will become more and more like the black curve. That's the idea. And if you graph this, let me tell you, you will have this and just bend up and you will get a parabola because it's a second degree polynomial here, and you will get like this. All right? And as you can see, when you have more and more terms, you will be able to approximate the curve with this polynomial better and better. That's the idea. One thing to notice is that though, when you have the radius of convergence, if this is equal to 1, well, you can also look at the interval convergence. Either way, you will be looking at from -1 to +1, right? -1 to +1. Let me tell you though, unfortunately for the best spread, no matter how many terms that you add, if you have infinitely many terms, the best thing that we can do is that this red curve is going to be like this, only covering this part. You can never use this curve and touch this point because this point is outside of the interval of convergence, unfortunately. So that's the idea, and I think this is enough for this video. Hopefully you guys all have a better understanding regarding what power series is all about, and you have a better understanding with the purpose of the power series. Seriously, it's just like having the decimal when you're trying to do computations with fractions or irrational numbers. That's it.